Thank you very much, Camp, and everybody for being here. The afternoon session is always the most difficult to capture the attention of the audience. I will try to do my best. And also, after 3 days of conference, we already told a lot, gave a lot of information, and probably also I'm sure part of what I'm saying has been already showed up. But I hope that I can add some new ingredients to our discussion regarding the behavior of this osmium double perovskite. In particular, I will talk about the doping by doing sodium-calcium substitution in this material, going from the D1 to the D2 material. So probably in the first part, I will show something which has already been shown. Let me first thank my very precious collaborators. Many of them are here. Vesna and Giuseppe Lodi from the University of Parma, Patrick Woodward, who provided us very nice samples to perform this work, and the group of Cesare mainly for the computational part, and also for the setup of this study, because I was very lucky. I must say this. Very lucky because we started to talk about that in 2017, probably, no? I was very lucky because at the same time, independently, I was starting to talk with Vesna, and Cesare came to Bologna, and so there was a very nice superposition of coherent superposition of states, and so this study started with us, Lorenzo and many other students helped us to do this job from the University of Bologna, Vienna, Brown, and from the Ohio University. So we have very good samples. We are looking at these good samples with mainly local probes, not only μSR and nuclear magnetic resonance, and everything is supported by very nice theory and computations. I would like to stress a little bit the fact that when we study typically emergent quantum behavior in matter, local probes are very useful, because typically in these kind of materials we might have electron inhomogeneities, phase competition, charge, lattice, spin, local distortion or modulation, and also dynamical local perturbation, quasi-particle excitation, for which the use of local sensor can give some more information regarding the behavior of these materials. And so we use nuclei and muon quantum particles to probe the state of matter in these materials. In particular, I would like to remind that the muon has a 1/2 spin, which means that it is mainly coupled to magnetic degrees of freedom. Not only, but for our purposes today, it is mainly coupled to magnetic degrees of freedom. It has a big magnetic moment, at least almost 10 times the neutron one, so it is highly sensitive. And in a standard dipolar interaction, we can think about the muon spin precession around a local field at the muon site. And we are able to detect these precessions through the oscillation typically in a muon signal. And we can detect the contributions to the local field. The nuclei can do the same thing by considering the magnetic spin, the magnetic moment of the nucleus. In addition, if the nuclei have a spin higher than 1/2, then they also have an electric quadrupole moment. And if this is big enough, typically they are a very nice probe, not only for magnetic properties, but also for electric charge related phenomena. So we can probe both charge, spin, but also orbital and lattice properties, which are coupled to all these quantities. Okay, so this is the method that we are using. And in particular, we were wondering what happened when we electron dope the Dirac-Mott osmium double perovskite that we have already discussed a lot during these days and today mainly, but also the first day. We have already seen this plot a lot of time, but it is important to stress the fact that with these double perovskites, we are typically in a condition where both lambda and both, so both the spin-orbit coupling and both U, the electronic correlation, electron-electron correlation are strong. Because this typically does not happen when you go through the periodic table, because typically when you increase the size of the ion, you are increasing the magnetic spin-orbit, the spin-orbit coupling, but you are decreasing U. But because of the double perovskite structure, as you very well know, here we have, we can see this also very naively from the chemical point of view, large magnetic ionic separation, and so the electron hopping is suppressed, and the correlation increases, strength increases. So this is a very nice material to study what happens when these two energies are competitive each other, and none of them can be considered negligible. So we are interested to substitute partially sodium by calcium until we end up with a full calcium series, and to study the interplay of electron correlation and spin-orbit coupling tuned by the charge doping. Okay. The two end members are already known. No, probably they not, but probably the first end member, the sodium, is now a good description of what is going on. And we know the magnetic structure. And for the calcium compound, the very former interpretation was a standard antiferromagnet material, but now we know that we have to consider also the multipolar character of these materials. And so by starting from this very famous paper from the group of Santini and Moretti in Parma, which was mainly dedicated to actinides, and where they started introducing these multipolar interactions in heavy elements. Nowadays, also in this conference, everybody is saying, okay, we should have in these materials the multipolar ordering. By the way, the authors of this paper, they don't know that nowadays we are still continuing to cite them so greatly because they stopped by studying this kind of topic. They now are studying other topics, and they when we discussed with them about to understand some point, they were nicely surprised about that. But it's okay. Now, these materials, we know that we accept now that there are Jahn-Teller distortions. Everything has been already well described, also from the theoretical point of view and from the experimental point of view. I would like to say that this is related to the fact that we are almost convinced, I think everybody here during these days was convinced that the system in the sodium is mainly non-cubic, and we should also remind again, for maybe after 100 times in this conference, that the first experimental observation of the fact that the system could be distorted, at least locally, was from Ba2Na in 2017 by this experimental report on nuclear magnetic resonance results on sodium, saying that the magnetic region is anticipated by local distortions in the phase diagram, which can be related to an antiferro-quadrupolar ordering in this material. Okay, Ba2Na continued by also studying better with this what kind of distortions are at play also from the experimental point of view. And this is possible thanks to the fact that in the NMR measurements, the sodium is coupled by hyperfine coupling to the osmium magnetic moment. And by NMR, it is possible to study the form of the hyperfine tensor. And if you have an isotropic symmetric situation, or almost isotropic situation, you typically have this result with a zero of diagonal terms, while in a more complex anisotropic spin exchange path, you expect to have something like that. And this can be measured by NMR. So, what about the calcium? What about the calcium? Most of us probably think that, okay, we already understood. It is ferro-octupolar. A lot of people have studied this in the last 2 years. And, but based on the fact that no structural distortion has been never found in this material. I don't know if we didn't search for it properly. We will talk a bit at the end of the talk also about that. Anyway, by doping the system with a sodium calcium solid solution, we checked that effectively we had effective charge doping by doing some experiments, and we also checked that there was a reduction as expected of the T2G-EG splitting due to the crystal field reduction in this material. So this is an effective charge doping in the system. And we also checked that the magnetic moment, the effective magnetic moment in the paramagnetic state is changing from 0.6 to about 1.6 Bohr magneton of the two end members. It's a monotonic increase, but it's not linear. You can see that there is a sort of saturation, somehow around 50% of calcium. And also the Curie-Weiss temperature changes. Here we know that it should be ferromagnetic because we have the canting that has been already discussed a lot in this conference for the sodium sample. And so we expect to have a slightly positive theta Weiss, Curie-Weiss. Why when we increase the doping, we add the doping, we are increasing the antiferromagnetic character because theta is going to be well negative. Okay, so everything works when we dope the system. And what is found is that the canting is suppressed almost immediately, because you can see also from magnetization measurements that here we have a kind of S shape, which is due to the canting, while it is almost negligible here for 12.5%, and then we completely lose the ferromagnetic-like character, and we only have a paramagnetic character. Okay, now, what about the local probes? By implanting muons, spin 1/2, mainly coupled to magnetic degrees of freedom, and by doing sodium NMR, which is coupled both to magnetic properties and to charge-related properties. Let's have a look to the results, and these are the μSR data. This is the sodium compound. The sodium compound, this is powder, a powder sample. But this is very good agreement with almost the same, with a single crystal results on the sodium title compound, here published in 2011. So the powder behaves in the same way. Okay, you can see that the oscillations are not very clear, even in the sodium. But we see that at low temperature, we have a magnetic state, because this signal is characteristic for a magnetic state, while in a non-magnetic state, you have this signal. The fitting function contains different contributions, some oscillations, oscillations, plus a very fast decay contribution, which is where the physical information is here in the exponent, which is related to the distribution of local fields as seen by muons. What does it mean? It means that part of the signal in these materials, depending on the implantation site of the muon, doesn't see a coherent oscillation, coherent precession of muons, which means that you have a sort of disorder, electronic disorder. Because the same is in the single crystal and in the powder. So it is not an effect of the powder nature of the system. Okay, so these are the information related here and here. This is related to the oscillation, related to the magnetic behavior of the sample. How does it change when you dope the system? Going from 0, so sodium, to calcium. You have something which is maybe similar to an oscillation, possibly. The receipt to fit the data is the same, but you see that there are not very convincing oscillation. At least one part of the signal is always a very fast decay, which means a sort of this disorder, but it means that you have a distribution of local magnetic fields. Okay, but through μSR you can measure very nicely where the magnetic transition occurs. And so this is the sodium, then a little bit of calcium, a little bit more, until we get the full calcium sample. And this is the magnetic volume fraction, which is always 100%. It means that the samples are good. And the magnetic transition temperature increases as a function of calcium. Okay. What about the magnetic state as seen by NMR? Okay, in this case, we have that the NMR spectrum for powders is respect to the high temperature, where we have a very nice single line, is much broadened. And this is the same also when we dope the system and so on, is broader than at high temperature. We can also distinguish, we can analyze in very detail the line shape at low temperature here in the magnetic state, and we can even detect what is the canting angle variation as a function of doping, which is canted here and almost antiferromagnetic soon after we dope the system by calcium. This is in agreement also with the magnetization measurements, the hysteresis magnetization versus field measurements. We are very happy about that. We can determine the hyperfine coupling and everything. And so we are happy that we can describe the magnetic behavior of the system as a function of doping. Now, we have something more, probably I was here the same, something more that in the intermediate phase before the magnetic state does occur, we have a slight change in the shape of the NMR signal, which is not anymore perfectly symmetric, but it is distorted. The fact that it is distorted is very easily seen if you plot the position of the peak and the position of the first moment of the peak. If the peak is symmetric, first moment of the distribution and position of the peak coincide. If they are distorted, then they are splitted. And so we can very nicely measure this splitting, let's say, temperature, which is the temperature below which the spectrum becomes distorted. Okay, very good. We can also do very nice fitting, simulate everything, and analyze everything, and obtain, and say that this is related to this broken local point symmetry condition, which was already observed in the single crystal for the sodium compound, and here is the same in the powder sample. Now, just to tell you that we have preliminary data also for the lithium material, and here, if you look at these curves, these are 13 Tesla, and we have a splitting. This curve and this curve, we have a splitting also here, anticipating the magnetic transition. Actually, we need to improve our feeding, etc., because with the lithium, the quadrupole moment is smaller than sodium, so the effects are typically lower. Anyway, this way we could detect through the distortion of the NMR peak that there is an anisotropy in an NMR shift tensor, which has orthorhombic local symmetry, which we interpret as the formation of a multipolar order, most likely of antiferromagnetic quadrupolar nature. And we could map the phase diagram that was already shown in the previous days, also by Arun the first day, where here we have the transition from the pure, we will talk about that, from the symmetric line shape and of the NMR signal, let's say cubic static condition, to this static distorted phase, anticipating the magnetic transition. So this way we demonstrated not only that we have a fast change from canted-antiferromagnetism to antiferromagnetic, but that the local distortions are persistent in the phase diagram, and also that the transition temperature increases very much when we are in the doped situation. But ask Marco, yes, please. Yeah. Yeah, you mean from the T1 relaxation time? I will talk very soon about the fluctuations, because this is the, let's say, the view which is more static or quasi-static in the scale of the NMR, which is hundreds of megahertz. I will come soon to the dynamical behavior. Okay. So anyway, just to remind what Marco was saying this morning, that anyway, even at high temperature, at room temperature, very fast probe can detect that there are dynamical Ian-Teller distortions. So probably what we are looking at here is that they are frozen in the scale of the NMR, which is typically a very slow scale, okay, so quasi-static limit. And now, what about the dynamics? this is very interesting because we have this effect that we can expect when we have some dynamical physical process with a characteristic frequency 1 over the correlation time equal to the Larmor frequency in an NMR. So we have this resonant condition. In this, if this condition is satisfied, then you expect that you have a large response of the system, which is measured by detecting the 1 over T1 relaxation time. And this is what we did. And we see that by measuring the system as a function of temperature, measuring the 1 over T1 relaxation time, we have a peak. This peak means that there is some fluctuating phenomenon which has a frequency at around 100 Kelvin of about 500 megahertz. This is the physical meaning of that. And by analyzing this behavior, we can, and by assuming that there is a thermally activated process, we can determine the energy of the barrier, the activation barrier of this process. And we can also measure by the amplitude of this peak the second moment of the amplitude of the perturbing field. And by comparing NMR, here is the NMR peak of the previous page, with µSR, we can see, okay, we have the critical fluctuating peak at the magnetic transition temperature, which is here. Then T1 display another peak, here is the zoom, which is related to these dynamics. Also the T2 display a peak at lower temperature because T2 is sensitive to the same dynamics, but at a scale, time scale, which is at a lower frequency. At a lower frequency. So the two peaks are related to the same dynamics. When we increase the temperature, the fluctuations increases, and then we first have a peak in T2, the transverse spin relaxation time, and then a peak in T1. Okay, so we discover a dynamical phenomenon which cannot be of magnetic origin, probably, because magnetic ordering is at very much lower temperature. And we have the proof of that by µSR, which is sensitive mainly to magnetic coupling, and we don't have any relaxation peak in the µSR results, only the peak at the magnetic transition, as it should be. So it means that these extra peaks are related to the charge dynamical phenomenon, which means that we have electric fluctuating charge perturbation, suggesting the presence of small polar quasi-particles. I must say that we didn't expect that from the experimental point of view. When we discovered the peak, by analogy with manganites, where the polaron exists and there is a similar behavior, similar activation energies, etc., we suspected that there was a polaron. And when I talked to Cesare, he told me also from our calculation we can see that there is the possibility to create to have polarons in this system, and we could measure everything as a function of the doping. You can see that the undoped material doesn't display these peaks, so probably the sodium counterpart doesn't have the polaron. And about this, Cesare and Lorenzo developed a very nice theory that Lorenzo is going to explain to you soon after me. So at the moment, I don't want to spoiler more than that, Lorenzo, about what you are going to say. And everything, anyway, is also recently published in this. And now, let me say just the last thing. What about what's happening at this end member? many references, but this is only part of them, studying this problem, but typically the argument is that the ferromagnetic octupolar should occur if the system is cubic, or while the antiferromagnetic quadrupolar if the system is distorted, right? This is the simple argument that we typically use. Now I would like to show you that we have two compounds with calcium. Nominally, they are the same. Both of them are cubic at high temperature with the same lattice parameter. You can see here this peak, which is the 620 Bragg peak. For both the sample and room temperature is at the same position. They have the same lattice parameter, the same structure. But when we cool down these two samples, let's call A old because it became fast, B new because it became later. The B, so this is at room temperature. When we cool down, the B sample has a single peak, which is simply shifted because of the shrinking of the lattice parameters temperature. But this sample at 4 Kelvin display a very nice splitting. Not very well resolved, but it is a splitting. So it means that it is in a tetragonal, structure. And so we can detect that this tetragonal cubic to tetragonal transition does occur around 50 Kelvin, close to the magnetic transition for this sample. Why for this sample? It is still cubic. The two samples have the same lattice parameters, no presence of this typical impurity for any of the sample, at least in the limit of detection of high resolution X-ray diffraction. The level of secondary phase generally small, a little bit higher for this sample, not that much. And they are not, they don't match any non-oxide containing combination of these. So formally they are the same samples. Whatever is the origin of this, now we are most interested to understand what is now the nature of the magnetic state in the tetragonal phase and in the cubic phase, probably from the experimental point of view. And so, unfortunately, we cannot do NMR. We are now preparing a sample with a 43 enriched calcium isotope because the natural abundant calcium isotope is not NMR active, so we cannot do NMR at the moment on the full calcium sample, but ɁSR can be done. You can see that the system which is cubic has a much more pronounced oscillation, while the spectral weight of the oscillating part in the tetragonal sample is lower. Here is the Fourier transform of these two signals. You can see that they are, the peak is at the same precession frequency, which means that the mean field probed by the muon is the same, but what changes is the coherence of these coherence length of the oscillation, of the precessions. This is very similar to what was already mentioned also this morning from this previous paper, and at least the one which is cubic, and they found it is cubic the same. And just to conclude, the magnetic volume plotted as a function of temperature for the two samples display that, okay, also maybe the magnetic temperature is changing slightly, but essentially, we don't see a very huge difference of the magnetic response of the sample. This is, in my opinion, an experimental evidence of the fact that whatever is the structure, tetragonal or cubic, the main feature features don't change that much. So now, ferro-octupolar or antiferro-quadrupolar, I don't know exactly how to give you a reply about that, but this is an experimental evidence of the magnetic response in tetragonal and cubic structure. which I think this is the conclusion. I think that we should consider, and it warrants further investigation. So these are my conclusions. The breaking of local cubic symmetry is driven by multipolar order, most likely of the antiferro-quadrupolar type, at least in this part of the phase diagram. We also have before that, I would like to mention the very nice talk of Arun, which developed the model, including considering the impurities in the system. As I told to Arun, if muons can be considered as impurities, probably we should expect that the magnetic transition temperature is different, while here you have the transition temperature from the muon spectroscopy and the one from NMR, they within the error, they coincide. Probably, I don't know if really the muons can be considered as particles which create some big effect in the system. Probably not. This is my experimental, from the experimental point of view, my view. We have to consider that we have the polaron, the freezing of polarons when we decrease the temperature. So this effect here, this whatever theory we are considering here, should consider that we have polaron, a frozen situation of polarons in the material, while this Jahn-Teller dynamical distortion might be driven by the opening of polaron, when at least we consider the doped system. This is still to be further studied, further understood about the end members of calcium. So I would like to thank you very much for your attention.